In this topic, we are trying to sketch the graph of a rational function. This time it doesn't have a slant asymptote, given its rule, and what they mean by rule is just an equation for this thing. So what this requires is to use our knowledge about rational functions to figure out where the horizontal and vertical asymptotes are, but then also to know what the slope is doing and what the concavity is doing on all the necessary ranges of values in this function. So we're going to need to find the first derivative to get slope. We're going to need to find the second derivative to get concavity, and then we need to look at first and second derivative to see if there are zeros there, so we know we have extrema or critical points, or we have inflection points. So it's quite a bit of work. Once you've done all that, then you actually have to plot the thing. So we're gonna try that. Our function here is negative 2x squared over 18 minus x squared. So I've got this up on the board here so we can do some drawing and try to make our derivatives happen. So let's start with a first derivative here, and I'm going to use the quotient rule. So I mean, you can always decide to use product rule by just changing the power here, but I'm going to use quotient rule. So let's see, this is going to be low, whoops, times the derivative of what's on top. So negative 4x minus what's on top, negative 2x squared, times the derivative of what's on the bottom, which is negative 2x, and all that's going to go over what's on the bottom squared. So that squared. Okay, so that's our first derivative. I think we can simplify this a little bit. Yeah, so when you put in negative 4 times 18, you're going to get negative 72 x, and then we're going to get a plus 4x cubed, and then here we get minus 4x cubed, so those parts go away. Actually, that's pretty nice. This is more simple than I thought it would be. 18 minus x squared squared. So this is our first derivative. So let's stop and think about this. Where is it 0, and where is it undefined? So it's 0 at 0. Yeah, so the point 0, 0 is going to be on the graph, and it's going to be a critical point. And then it's also going to be undefined, and where it's undefined is the same as where it's undefined in the main function. It's where x squared equals 18. So that means where x equals plus or minus the square root of 18, which is plus or minus 3 times the square root of 2. So those are also critical points because the first derivative is undefined there. I guess the second derivative is going to be undefined there too. Maybe we should go on to figure out the second derivative. And this gets a little hairy, I think. Always applying the quotient rule more than once, numbers get big and so forth. So we're going to have low d high. So 18 minus x squared quantity squared times the derivative here, which is just negative 72, minus high, which is negative 72x, times the derivative of what's on the bottom. And we're going to use the chain rule for that. So we'd say u equals 18 minus x squared, and then we'd have u squared. So we want derivative of u squared, which has to be times the derivative of u. So we're going to do 2 times u, which is 18 minus x squared, and then times the derivative of what's inside here, which is negative 2x. So that all gets multiplied on here. So 2 times 18 minus x squared and times minus 2x. And then all of that goes over what's on the bottom squared, which is 18 minus x squared squared. You square that again, you get it to the 4th power. So there is definitely some simplification we can do here. One thing I'm noticing is that there's this factor everywhere. So I can cut that down by 1. I can divide by 18 minus x squared. On the bottom, that's going to give me 18 minus x squared to the 3rd power. And then on the top, I'm going to get 18 minus x squared times negative 72. And then poof, up here, this will go away, and I just get all of this stuff. So what is that going to be? I think we're going to get 288, negative 288. Yeah, that's going to be, well, with this minus, it'll be negative. So negative 288 x squared. And then can we simplify that some more? If we multiply the 72 through here. Oh yeah, so we're going to get negative 288 x squared plus 72 x squared minus 1296. All of that is still over 18 minus x squared cubed. And this simplifies to 216. So negative 216 x squared minus 1296 over 18 minus x squared cubed. So I think I may have made a mistake along the way. It's possible, but I think this is our second derivative. And let's think about this. So it's going to have the same undefined points that positive and negative square root of 3, or 3 times the square root of 2. So those are critical points where the concavity can change. I'm looking for zeros, and I don't think we're going to have any here because, yeah, it would be, we'd add 12, if we set this top part equal to 0, you'd add 1296 to both sides, then you'd divide by a negative 216, and you'd get have to take the square root of a negative number. So those would be imaginary zeros there. So looks like don't have to worry about the zeros for the second derivative. Okay. I think we have the information we need. We're going to come back and refer to all this chicken scratching as we try to build the graph, but let's do some graph building. I think the first thing to do is plot the asymptotes. And we already noticed that there are vertical asymptotes at negative 3 times the square root of 2 and 3 times the square root of 2. So we'll put those in. Okay. Now, what about the horizontal asymptote? We're told this is not a slant asymptote, and actually we should know that because the highest power on the top and the bottom is the same power. When that's the case, your horizontal asymptote is the line y equals the ratio of the coefficients of the highest power. So this would be negative 2 over negative 1, which is a positive 2. So the line y equals 2 is going to be our horizontal asymptote. Okay, and I think that's everything for the asymptotes. We also noticed that we have the point 0, 0 on here. If you put in 0 for x, you get 0 for the function. So let's go ahead and plot that point, 0, 0. And that point is also a critical point for the first derivative. So there's probably a local, probably a local max looking by the way these asymptotes are looking. All right, and I think we've got all of those undefined points and our extrema on here. So we just need to determine slope and concavity. So we'll go through here and we'll test some values. Now, 3 times the square root of 2 is like a little over 4. So we can plug in a negative 5 and a positive 5 to test those. We'll maybe plug in a 1 and a negative 1 to the first derivative to get slope, and then to the second derivative to get concavity. In the interest of time, I'm going to show you because I've done that ahead of time to make sure that works. So we've got a positive slope and concave up over here. And I found that by plugging in a negative 5 into the first derivative and the second derivative to get positive and positive. Then we've got positive slope concave down here and negative slope concave down here. And I got those values by plugging in a 1 and a negative 1. And then we've got, we've got kind of the mirror image over here with a negative slope and concave up. Go ahead and verify that by plugging those values into what we got for the first derivative and the second derivative. But this should be it. I'm just going to, before I run out of time, quickly check it. And there it is. So that is how to graph a rational function.